Right. Let's unpack this. Today, we are really getting into something fundamental, something that underpins almost every GNU Linux system out there. We're talking about the file system. It's kind of the unsung hero, right? The thing working silently in the background, deciding how all your data gets stored, tracked, retrieved.
Exactly, and the specific one we're zeroing in on is the Fourth Extended Filesystem, EXT4. Chances are, if you're using Linux, this is what's managing your storage. Its whole reputation really isn't about flashy new features. It's built on being dependable, stable, just plain mature technology.
And that's the interesting tension here, isn't it? That's what we want to dig into. Our mission today is, well, to trace its whole family tree, basically. See how EXT4 evolved from these really humble beginnings, why it's been such a mainstay, this battle-tested workhorse. But also, we need to look hard at the trade-offs. What do you give up when you stick with mature tech in a world that's, frankly, asking for more modern stuff like advanced data integrity? We're giving you the shortcut to really getting this essential piece of the puzzle, warts and all.
Yeah, and the key thing to grasp about EXT4 is that it's all about evolution. It wasn't some radical rewrite. It's the end result of this long line, stretching back, over 30 years? And each step, each version, was really just fixing a big practical problem its predecessor had.
Right. So to really appreciate this workhorse, we kind of have to start way back with the pony. The MINIX file system in '91. Linux actually started out using MINIX. It worked, sure, but looking back, it was almost comically limited.
Oh, absolutely. We're talking about partition sizes capped at just 64 megabytes. And file names, you got 14 characters.
Right.
Max. It just wasn't built for where Linux was obviously heading, even back then.
So that limitation pretty quickly led to the first extended file system, EXT, and then the real king of the 90s, EXT2, that came out around 93.
EXT2 is huge. Simple, fast for its time. It really powered Linux's growth, especially in server rooms. But it had this one massive flaw, a real Achilles heel for admins.
The journaling thing, or rather the lack of journaling.
Exactly. It was non-journaling.
And for anyone running a server, what did that actually mean day to day? Or maybe night to night when things went wrong?
It meant disaster if the power flickered or the system crashed, because when that machine rebooted, the OS had absolutely no record of what disk operations were finished and which were, halfway through.
Chaos.
Pretty much. It had to do a full, slow, painful file system check. SWIC. Maybe on a small drive, say 4 gigs, that's 10 minutes of downtime. Annoying, but okay.
Yeah.
But if you were running one of those early, terabyte arrays, that check could take hours.
Hours of just watching a progress bar crawl across the screen while your critical services are completely dead in the water. I bet that cost some sleepless nights.
Oh, definitely. That downtime, that flick wait time, that became the big availability headache of the late 90s.
Okay, so the community obviously needed something better, something that can maybe build on EXT2, keep compatibility, but kill that horrendous recovery time.
And that solution was EXT3, which landed in 2001. And its absolute killer feature was, you guessed it, journaling.
Journaling. Let's break that down a bit. How did that change the game?
It changed everything for reliability. You can think of the journal as like the file system's private to-do list. Before it does anything major, like moving a file or updating its records, it writes down its intention in this special log, the journal. So if the power cuts out mid-task, when the system boots back up, it doesn't need to scan the entire disk anymore. It just reads the journal, sees the unfinished jobs, and can either quickly complete them or roll them back cleanly. No more hours-long checks.
That is a massive, massive improvement. Huge for uptime. But, okay, they solve the stability crisis, and then what happens? Disks just keep getting bigger, right?
Exactly. Scale becomes the next problem. EXT3 was solid, but by the mid-2000s, with disk sizes exploding and people talking about petabytes, EXT3 started to show its age. It wasn't designed for that kind of scale.
Which brings us to EXT4, stabilizing around 2008. The goal here was what? Keep that EXT3 compatibility, which was crucial for adoption.
Absolutely mandatory, yeah.
But make it handle file and volume sizes that were just unimaginable a few years earlier. So it's really the ultimate evolutionary step, taking that proven foundation and tuning it for sheer size and performance.
Precisely. Taking the best of EXT3 and making it ready for the future, or at least the future as they saw it then.
Okay, here's where it gets really interesting, especially when you talked about the scale EXT4 was built for. The numbers are just wild.
They really are. The limit for just one single file jumped up to 16 terabytes.
16 terabytes for one file. And then the volume size.
Up to 1 exabyte, 1 EIB.
And an exabyte, that's what, 1,000,000 terabytes? It's one of those numbers that just breaks your brain a little.
It's huge. To put it in perspective, think about filling up a 1 exabyte volume. You'd need more than 65,000 of those massive 16 TB files just to fill it.
That's the kind of data architecture we're talking about here. Just staggering.
And managing data on that scale, you can't do it the old way. It needs a fundamental change in how the file system tracks where everything is, which leads us right into its big performance win.
Extents. Okay, this is important, but can be a bit abstract.
Yeah.
How did extents make things faster compared to how EXT2 and EXT3 did it?
Right, so under the older system, the block mapping system, imagine you have a large file, maybe it takes up 1,000,000 blocks physically next to each other on the disk. EXT2 and EXT3 had to create 1,000,000 separate little records in their metadata, basically pointers, one for every single one of those 1,000,000 blocks. That's a ton of bookkeeping.
It sounds incredibly inefficient, like a librarian having to write a separate catalog card for every single page in a 1,000-page book.
That's a great analogy, yeah. Extents fix that. Instead of tracking each individual block or each page, an extent tracks a whole range of blocks that are right next to each other. So using your analogy, the extent just says, this file uses pages 1 through 1,000,000, one record instead of 1,000,000.
Okay. So it drastically cuts down on the amount of metadata the file system has to manage, especially for big contiguous files. Makes reading and writing them much faster.
Much faster, exactly. Less overhead.
Makes total sense for things like large videos or database files. Now, the other big performance trick was something called delayed allocation. How does that work? Sounds a bit like procrastinating.
It kind of is, but in a smart way. Delayed allocation, or DLALOC, is about performance. When your application says, hey, kernel, write this data, the kernel doesn't immediately rush to find disk blocks and write it. Instead, it holds that data in memory for a short while. It buffers it.
Waits. Why wait? Isn't that risky?
It introduces a small risk, yes, and we absolutely need to talk about that. But the benefit is better performance and less fragmentation. By waiting just a little bit, the kernel can gather up several write requests, look at the data, organize it, and then write a much larger, more continuous chunk to the disk all at once.
I see. So instead of lots of little scattered writes that fragment the file, it does bigger, cleaner writes, more efficient, less messy.
Exactly. It's a very effective way to reduce fragmentation as files are being written.
But let's circle back to that risk you mentioned, because that seems like a serious trade-off. If the system crashes after the application thinks the write finished, but before the kernel actually flushed those delayed buffers to disk, what happens?
You could lose data. You might end up with an empty file or a partially written one. The application got the success message, but the data never actually made it physically to the disk platter.
Ouch. So speed comes at the cost of a small window of potential data loss if things go sideways unexpectedly. That's definitely something to be aware of.
It is. It's inherent to how delayed allocation works. Okay, moving on to reliability improvements. EXT3 gave us the journal, which was huge for crash recovery. EXT4 added another layer on top of that. Journal checksums.
Right, checksums. This feels like getting into the weeds, but it sounds important. EXT3 recovered quickly, so what did adding checksums to the journal itself actually achieve?
It protects the file system's own internal bookkeeping, the metadata. Think about it. The journal is your recovery guide after a crash. What if the guide itself gets corrupted?
Like a typo in the recovery instructions.
Precisely. Maybe a memory glitch or a bad disk write corrupts an entry in the journal file itself. If the system blindly replayed that bad instruction, it could scramble the file system's metadata, potentially making things much worse, like losing the map to where your data is.
Okay, I see. So journal checksums basically validate those recovery instructions before executing them? A safety check on the safety net.
Exactly. It prevents a corrupted journal from causing metadata corruption. It's a critical internal safeguard.
And practically speaking, for sysadmins, EXT4 seems like it smoothed out some rough edges, too. You mentioned FIS gets faster.
Significantly faster in many cases, yeah. Because the file system knows more about its own structure, FIS can safely skip checking areas of the disk, the block groups, that it knows are completely empty or unallocated. Less work to do.
Less downtime waiting for the check to finish.
Right. And maybe even more useful for busy systems, EXT4 added support for online defragmentation. There's a tool, E4 defrag. It means you can try to tidy up file fragmentation on a mounted active file system.
Yeah,
You don't always have to schedule downtime just for that kind of basic maintenance.
Okay, so we've painted a picture of a very robust, scalable, and practical file system. But now we have to look at the downsides, the wrinkles that come with age. EXT4 is stable, it's reliable in that classic sense, but you said its age is its main weakness now.
I think so, yeah. It really represents the peak of that particular design philosophy, that evolutionary line. But that classic design just doesn't have room for features that are, well, frankly, expected in newer file systems like BTRFs or ZFS.
And the biggest missing piece, the one that really hits home when we talk about modern needs, seems to be around data integrity, that gap.
Absolutely. This is, for many people, the fundamental issue with EXT4 today.
Right.
We just talked about how journal checksums protect the metadata, right? The file system's internal map. But EXT4 does zero checksumming, no integrity checks at all on your actual user data, your documents, your photos, your code, nothing.
Hold on. So after all these years, all this development, if I'm running EXT4, the file system itself has literally no way of knowing if the file it's giving me is the same file I originally saved. The bits could have flipped somewhere.
That's exactly right. It leaves the system completely vulnerable to what's often called bit rot, or silent data corruption. You know, a stray cosmic ray, a minor glitch in the disk controller, the storage media slowly degrading over time, a bit flips somewhere in your file. EXT4 reads it, hands it over, and has no idea anything is wrong.
Wow. Okay. So you have this incredibly reliable file system famous for surviving crashes, but it might be silently feeding you corrupted data without ever throwing an error. That's genuinely unsettling, especially for critical archives or backups.
It really forces you to reconsider what reliability means. For EXT4, it means the file system structure is likely to remain consistent and recoverable after a crash. It does not mean the data within that structure is guaranteed to be accurate over time. Modern systems like ZFS or BTRFs tackle this head-on. They checksum every block of user data, usually storing that checksum with the metadata pointer. So when you read the data, they recalculate the checksum and compare. If it doesn't match, alarm bells ring. They know it's corrupt and ideally can even fix it if there's redundancy. EXT4 just can't do that.
That's a fundamental difference in philosophy, it sounds like. Beyond that huge integrity issue, what other sort of modern features are just missing, forcing admins to bolt things on?
Well, the big one is probably the lack of native snapshot support.
Snapshots. Right, those instant point-in-time copies.
Exactly. They're incredibly useful for backups, for rolling back changes quickly, for testing things without risk. Modern file systems often have this built in, very efficiently.
Whereas with EXT4, if you want that kind of snapshotting, you need to bring in another layer, right? Like using LVM, the logical volume manager, to snapshot the entire block device underneath the file system.
Precisely. It works, but it's external. It's another layer of complexity to manage, rather than being an integrated, efficient feature of the file system itself. And it's the same story for things like transparent file compression or built-in data encryption. With EXT4, you're generally relying on other tools, maybe file system-level encryption like fscript or application-level stuff, not something the file system handles natively from the ground up.
And let's quickly touch on administration again. We said Flisk is faster on EXT4, which is great. But that one painful limitation remains, doesn't it?
It does. It's still an offline operation.
Yeah.
To run a full check and repair potential errors with Flisk, you must unmount the file system first.
No way around that.
Not for a full, proper check and repair, no. So even if the check itself is quicker now, taking that file system offline, even for minutes, well, for truly critical 247 services, any downtime is significant downtime. Modern designs often aim for online scrubbing and repair, trying to eliminate that need for offline maintenance windows entirely. EXT4 just isn't architected for that.
So what does this all mean? Let's try to synthesize this. For you, the listener, running Linux, probably on EXT4 right now, what's the takeaway?
It means you're likely running on something incredibly stable, battle-tested, and reliable in terms of its structure holding together. EXT4 is fast enough for most things. It absolutely solved the biggest headaches of its predecessors, especially that awful crash recovery time. You're unlikely to have the file system itself just suddenly break catastrophically.
And it's a big but. It's fundamentally a design from the 2000s, built for priorities of that era. And the conversation around storage has shifted, hasn't it?
It really has. The focus now, especially with ever larger data sets and longer retention times, is increasingly on guaranteed data integrity, on flexible management like snapshots, on features EXT4 just wasn't built to provide natively, checksumming, self-healing. That's where newer designs are focused.
So EXT4 is the peak of its evolutionary path, but maybe that path doesn't lead to where storage needs are heading now.
You could definitely argue that. It forces a fundamental choice on people designing systems today. Do you prioritize that rock-solid, proven stability of EXT4? Or do you prioritize the built-in data integrity and modern features of something newer, maybe accepting it's less battle-tested? Stability versus integrity.
Which leaves us with a really interesting question to chew on, doesn't it? If EXT4's biggest strength is its incredible stability, its resilience, built over decades, and yet its biggest weakness is this inherent vulnerability to silent data corruption, to bit rot, because it doesn't check user data. How do you, as a system architect, make that call? When does the comfort of guaranteed stability outweigh the fundamental need for built-in integrity checks, especially for data you absolutely cannot afford to have silently decay?
Is the risk of undetected corruption a price worth paying for the near certainty that the file system structure itself won't let you down during a crash? That's the tough question EXT4 forces us to confront.
A very deep dive indeed into a choice many people make without even realizing it every time they format a drive. Keep learning, keep questioning those assumptions, and thanks for taking this deep dive with us.